In this video, we're going to continue our qualitative discussion of phase transitions. Okay, now here we have a PVT surface here, and at the critical point, the gas and liquid have the same density and specific entropy. Okay, so what used to be down here in this coexistence region, the transition from gas to liquid used to be first order. There'd be a sudden change. For instance, going from gas to liquid, you have a sudden jump in the density, okay, or a sudden decrease in the density in that case. At the critical point, the gas and liquid have the same density and specific entropy, and the transition becomes second order, okay. And so here we see the pressure versus temperature graph for these things at a fixed volume, and you can see, for instance, the solid phase and the gas phase separated by a very clear line here. But as we've seen before, if you go around the critical point, you can go from gas to liquid, and that's what we did before. Okay, there's also something else in our sort of classification called the triple line and the triple point. Okay, so here we have liquid and vapor coexisting, and here we have solid and vapor coexisting, and if you're along this line just here, you're on the triple line, and there gas, solid and liquid coexist with each other. Okay, if you're in the pressure temperature plane, this becomes a point, which is just the triple point, which is just there. Okay, so for the triple line, you get gas, solid and liquid coexisting with each other. Okay, all three of them together. Okay. All right, we're going to leave the PVT diagram for a bit and talk about latent heat. Now, latent heat is hopefully something you already know about. If you convert, say, liquid water to steam at some temperature, which is normally 100 degrees, the specific entropy of each substance is different. Okay, so S per mole of steam is different from S per mole of water. What this implies, because remember, dq is T ds, okay, this implies that we must add an amount of heat merely to do the conversion, okay? So you must add an amount of heat which is equal to, per mole, this amount of heat must be equal to the temperature times the difference in specific entropy of the steam and the water, okay? And that thing is called the latent heat. And that heat is often very, very large. There's a famous experiment you can do where you walk into a lecture hall with a kettle, okay, and you plug the kettle in and switch it on. It's full of water, and basically after a minute or two, it starts boiling. So it doesn't take very much energy to change the water from say 20 degrees to 100 degrees. Okay, it starts boiling. But of course, after that, all you're doing, if you manage to disconnect the automatic switch off for the kettle, all you're doing then, as you keep adding heat, is you're taking the water, the H2O, liquid H2O, and converting it into steam. Okay, and you can go for the whole lecture just watching this thing convert liquid water to steam, and it doesn't finish. Okay, and that's because this latent heat for water is enormous. Okay. All right. So what happens with latent heat is that usually, if you increase if you apply some heat to the system, it increases the temperature of a body. But here it does not. Okay, it just makes the body undergo a phase transition. And the English word latent comes from Latin latens, meaning lying hidden. Okay, and the term latent heat was introduced in calorimetry around 1750. When a Scotsman, Joseph Black. Now, a lot of the contributions to thermodynamics come from Scotsmen for some reason. And this one was done by Joseph Black, and he was commissioned by the producers of Scotch whisky in search for an ideal quantities of fuel and water for the distilling process. And in the thinking about this, he discovered the idea of latent heat. Okay, so there's Mr. Black there. All right, so if we have coexistence of phases, liquid and vapor, or they are coexisting at the same pressure and temperature, we're going to minimize the Gibbs potential. Okay, So, and we've talked about chemical potentials before, and we said you have to equate the chemical potentials. Let's try and prove that here. So we've got N is our total number of particles, M1, N2, the number of particles in each phase. So this might be in vapor, this might be in liquid, okay? But we have this being true, okay? Mu I, PT, is the chemical potential of phase I. It might be water. Sorry, chemical potential in phase I for the water molecules. It could be liquid or it could be gas, okay? This is the Gibbs potential per particle. So the total Gibbs potential is easy. It's just the sum of the Gibbs potentials for each of them. So we put 1 there. It's missing. Okay. And because N1 plus N2 must equal N, we can write the Gibbs potential just in terms of N1. And we're going to minimize everything over N1. And what do you know? If we minimize over N1, we get mu1 equals mu2. The chemical potentials in each phase are equal. So if you have water vapor and liquid water, the chemical potential per molecule must be the same in each of those phases, which is what we used before, or at least discussed before. Okay, even though the chemical potentials are equal, which is what we just showed, other things jump, okay? So du mu dt at constant P, which is the specific entropy, jumps, as does du mu dP at constant T, which is specific volume, okay? They jump across the phase span, and that's bloody obvious. It's bloody obvious that the volume per molecule in steam is much larger than the volume per molecule in water. The entropy might not be so obvious, but it's still fairly clear there's a jump there because the steam is exploring much more volume. Okay. All right. Just briefly, we'll mention something which you must have seen before, which is the Clapeyron equation, and this tells us how the pressure varies with temperature or vice versa as you go along a coexistence line, okay? And we're not going to derive it here. You can look at the textbook to derive it. But it tells you that the P dt is equal to the latent heat divided by the temperature divided by the specific volume. Okay, it's jump in specific volume. Okay, and from that you can figure out how, for instance, the temperature of a phase transition varies with pressure, for example, with the boiling of water, for example, or something like that. Okay, and there are two different cases whether you get the liquid contracts or expands on freezing. So contracts when CO2, for instance, contracts when it freezes, which is the normal kind of behaviour. Think of things getting smaller when you freeze them. But water, of course, expands on freezing, and you know that because ice floats on top of water. Okay, normally icebergs float on the top of the ocean, and ice floats in a drink. Okay, so let's look at real gases very briefly. Okay, so you know this particular figure which we've seen before, which is the energy of interaction between two molecules as a function of the distance between their centres. And there's a minimum here, but typically, of course, the particles are way out here somewhere. They're not. The system is not that dense. You're not at the minimum because basically it's a gas. Okay, so the first person to really look at real gases in a convincing way was Clausius, and he said, right, because real gas molecules actually take up some volume, we should take this thing PV equals NKT and reduce this volume, because the volume that this thing can move to is actually less because it's going to hit some of these molecules. And so we're going to reduce the volume by this thing B prime, which is just the number of molecules times sort of more or less the volume of a molecule, okay, or something close to the volume of a molecule. Okay, so he came up with this equation here, which is a correction to the ordinary ideal gas law, and R naught here is some molecular size. That makes a lot of sense. And then van der Waals came along and made another correction, and van der Waals said the pressure against a wall is reduced because the molecules attract one another. So here's my wall, and ordinarily, the pressure would be due to this guy coming in and colliding and bouncing off. But in fact, when he comes in and collides, there's other molecules here, and so he comes in a little bit differently because the other molecules are attracting him already. He doesn't hit this thing quite so hard. So the pressure is reduced by that factor, And if we have n moles, you will find that's the reduction in pressure. Now it looks like I've added something to the pressure, but of course what this means is on the other side, if I put the pressure solve this for the pressure, I would find a subtraction over here. So pressure would equal something which is minus. So that's why it looks different. And the reduction in pressure is proportional to the density squared. And in fact, Laplace first did this a long time ago in the 18th century. Okay, he first maybe very early 19th century with Laplace. Okay, he first didn't quite derive the van der Waals equation, but he said the reduction in pressure should be that. Okay, you often find there are people who've done the thing well before it's considered to be really important. So, and then of course you get the van der Waals equation of state, which is that one. Okay, which is the work of van der Waals and Clausius. Okay, another thing we need to talk about is this video is about a whole lot of little technical stuff, bits and pieces, which you will find useful at some stage. The viral expansion. Okay, in thermodynamics and stat phys, this is an expansion in the density. Okay, so for ideal gases, we normally just write that, but for real gases, we write this, PV on nRT is equal to 1, which is what you get for ideal gases, plus corrections due to the density, due to the fact that the molecules are interacting, and that's proportional density, density squared, blah, 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 blah. And Ci is the ith virial coefficient and takes into account the interactions between the molecules. So as an exercise, you should go away and calculate C2 and C3 for a van der Waals gas. This effectively is an expansion of the equation of state in the density, or in powers of the density. So first power, second power, etc., etc., etc. So go away and calculate C2 and C3 for van der Waals gas and see if you can get it. All right, so talking of van der Waals gases, let's look at what happens at different pressures and volumes and temperatures. So we can take 1 mole of van der Waals gas, and this will be our equation, where P and B and A are constants. Okay, so we're going to fix the pressure and solve for V, which is a cubic. So and we're going to draw different curves at different T. So here's a curve at high T, here's a curve at low T. It's a curve at the critical temperature, okay? And we're going to fix the pressure and solve for V. So if I fix the pressure up here at this particular temperature, say, oh, well, there's only one solution for V, which is there. If I go down to low T, I will get a curve looking like this. And I need to actually take this curve and expand it. So I need to go further and further and further like this. Okay, it'll go down like that. Okay? So if I go to low T and low P, down here, this is my P, I've only got one solution, and that's a gas. So the solution I would have is where those two intersect for a given pressure. I get a volume which is there, okay, and that's a gas, big, very large volume, right? Which means per molecule, which is a gas. Okay, if I go to slightly higher P, I'm going to go up here, and what I find are 3 solutions. One which would be a gas, and one which would be a liquid, which would be here, I suppose, and one which was completely unphysical. Okay, the van der Waals equation is not perfect, it would sometimes produce really weird solutions. If I go then to higher temperatures and pressures, up here, I only get back to one thing, which is a gas. Okay, one solution. For that P and that T, I'm going to go that volume, which is a gas. Okay, but you can call it a liquid because we're above the critical temperature. There isn't a distinction. Here there might have been a distinction between that and that. There was a clear density distinction. Here, what does that mean? Was it a gas or a liquid? I don't know. No one knows. I mean, it's not a thing you can make any distinction about. Okay, so in the van der Waals system, you can actually figure out what the critical point looks like, what the pressure, temperature, and volume are, and you can write the critical pressure. You can scale the pressure by the critical pressure, the critical temperature, and the critical volume. So what you do is you take the pressure, divide by the critical pressure, take the temperature, divide by the critical temperature, take the volume, divide by the critical volume, and the van der Waals equation then has this universal form, which doesn't involve any of these weird constants A and B, but it does mean that pressures and volumes and temperatures are scaled by the critical pressure, okay, and temperature and volume. Okay, and you can ask, the question to ask is, okay, we know Van der Waals equation works somewhat, but not perfectly. Does this scaling work does this scaling equation work? And the answer is no, but you can still scale the data for different gases with the measured pressure, temperature, and volume at the critical point. And when you do that, you end up with a very nice curve that looks like this. This is the density divided by the density at the critical point. This is the temperature divided by the critical temperature. And all the gases, well, not all of them, but most of them, actually lie on a given universal curve. So neon, must be argon, I suppose, krypton, xenon, nitrogen, oxygen, etc., etc., etc. You can see neon's a bit off, but they all pretty much lie on the one curve, and that's called scaling, and it's very, very useful, not just in thermodynamics, but in almost all areas of engineering. For instance, you scale things, and you can get everything to lie on a universal curve, which is very, very useful. Okay, so this tells us something that basically, the fact that all these all lie on the same curve tells us sort of about the universality of the interactions of molecules with each other. Okay, and the details of the interactions probably don't matter very much. All right, I'm going to finish off by looking at transition dynamics. So, nucleation versus spinodal decomposition. Okay, so we look at these free energy curves here. This is free energy versus, say, density. Okay, there are two kinds of behavior we can find. Okay, if we start at a very high temperature here, this is very, very high up here, and quench so that T is just below Tc, so here. Okay, so just below here. We start off with, we've got one low density minima, and then when we quench, we'll get a second minima at a higher density if we lower the temperature. But what you will notice is, even though this one has the lower free energy, because this thing's gone below the axis, what you will find is there's a barrier. It has to go over a barrier. Okay? And when you have to go over a barrier, you have to wait a long time, because to go over that barrier, you need a nucleation to occur. The system has to decide, oh, actually, it's good to be dense. Okay? And so, because of that, you can supercool water, for instance, below the freezing point. If you get some very pure water and it's not full of horrible bits of rubbish, okay, you can supercool it below the freezing point, below 0 degrees, and it will not freeze until it forms a nucleus, and then it will all freeze at once. Okay, so it can be supercooled for a long time, and then suddenly a nucleus will form, and suddenly the whole thing will freeze. So that's nucleation. Okay. There's another kind of dynamics you can do, which is you start at a high temperature and there's only one minima, okay, which is the low density minima, and suddenly you can quench it well below the critical temperature, okay, well below the temperature at which it will form the dense phase. And when you do that, there are no barriers to nucleation. So you cool at this temperature here. There's this, suddenly this minimum appears, and basically the system spontaneously forms the dense phase, and the only thing which changes the dynamics here, which limits the dynamics, is that stuff has to diffuse into the dense phase. You've got a dense phase here, you've got some non-dense phase, you've got the dense phase starting to happen, and stuff has to diffuse into the dense phase, and that is called spinodal decomposition, with different kinds of dynamics. And here we see a system of different kinds of particles. They're blue and red here. And in spinodal decomposition, these are some computer simulations, which we'll actually go into later on when we discuss phase transitions towards the end of the course. You will see this kind of pattern forming, where you get typical spinodal decomposition looks like this sort of continuous red and blue interpenetrating kind of system. Whereas it started off, the red and blue are fully mixed up here. Okay, and these different sort of systems will be for different amounts of red and blue. Okay, and that's what spinodal decomposition looks like, and we will finish there.